Hello everyone, and welcome to today's webinar. Before we get started, I would like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you would prefer to join over the telephone, just select Audio Options and leave Computer Audio, and then dial in the telephone number displayed. You will have the opportunity to submit text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation, and we will collect these and address them during the Q&A session at the end of today's presentation.
Thank you, Clara, and thank you to everyone for joining us today for the conclusion on our series on all you need to know about modern hipping. My name is Nikki, and I will be the moderator for today's webinar on high isostatic pressing and high pressure heat treatment for additive manufacturing. Presenting today, we will have our application specialist, Magnus Olfers. Magnus, if you would like to introduce yourself and tell everyone exactly what it is that you do at Quintus.
Okay, sure. So my name is Magnus Olfers. I'm an application specialist for hot and cold isostatic pressing. I've been with Quintus for 5 years now, and I'm originally from Sweden, but since August last year, I'm based at our US site in Columbus, Ohio.
Thank you for that, Magnus. Just a reminder, if you have any questions for us throughout the webinar, please feel free to ask them in the side panel, and we will try to get back to you during the Q&A session at the end, or at least within the next day or so. I also want to inform you that you'll receive all the materials presented in this webinar, as well as the recording within 48 hours. So Magnus, why don't we go ahead and get started?
Okay, thank you, Nikki. So here we can see the outline of today's webinar. So I will start by talking about hipping for additive manufacturing material in general. Then we will discuss a little bit about different defect types in AM material and how this can have an effect on the hipping. Then I will go through 2 case studies, which I think is very good to show the relationship between processing, microstructure, and properties for AM material. So that will be optimized HIP parameters for EBM Ti-6AI-4V and optimized printing parameters for hipping. And then I will end up with a summary. But first, if we start by looking at the full process chain of metal additive manufacturing. So, of course, the printing process have a very important part is because it's, of course, here where we're creating our parts. However, the other process around the printing is also of great importance when it comes to the final properties of your part, to be able to produce part after part with the same properties, and to be able to inspect and qualify and certify parts. So, of course, we also have powder feedstock, where we might look at chemical composition, powder morphology, etc. We have the printing process, of course, printer make, model, print parameters. We have thermal post-treatment like stress relief, HIP, heat treatment. We might have a surface treatment of our parts by machining, blasting, chemical milling, etc. And there might be some inspection afterwards for the geometry, the tolerances, X-ray CT scanning, material testing, etc. And one good example of a company that's really understood the importance of looking at the full process chain for AM is Sintavia in Davie, Florida. So they are an end-to-end AM process manufacturer, and they have in-house capabilities within design, powder analysis and characterization, metal printing, hot isostatic pressing and heat treatment, X-ray CT scanning, mechanical testing, including fatigue, creep, and high temperature tensile, metallography, and they have full accreditation. Now I'm going to go in a little bit about hipping for AM material in general. So if we look at the as-printed material, we will have some internal defect in the as-printed state. The amount of defect will depend on printing parameters, the alloy that we're working with, the powder, etc. And there will be different types of defect depending on where they originate from. And these internal defects, they will act as stress concentration and crack initiation points in the material, and this will negatively influence your material properties. So by going through the HIP process, we will eliminate these internal defects, and by doing that, we will eliminate, of course, the stress concentration and characterization points to get improved material properties. So, for example, we often see a very big increase in fatigue performance of HIP material. We also see increased ductility and fracture toughness of material. Also, since we're reducing randomly distributed porosity in the material, we normally see a reduction in property scatter. So we get more predictive material properties, so we can use design values closer to the actual strength of the material. We can also see improved quality in machine and polished surfaces. We can see an example here on the right. In this picture on the left, we have as cast ingot that has then been machined. And as we can see, we have a revealed internal porosity in the surface here. So this is not very good. On the right here, we have the same type of casting, but we have hipped it before machining. And here we can see a virtually perfect surface. So this is quite important when it comes to corrosion properties, optical properties, any type of sealing application, and also aesthetical properties. For example, hipping is actually used within the jewelry industry and luxury watch industry, where they are hipping MIM parts and casted parts to be able to produce very perfect surfaces. One thing I want to point out as well is that strength is mainly determined by microstructure and not defects. So if you're looking to get the HIP process done to increase the strength of your material, you might be disappointed. However, in a modern HIP system, we can incorporate all kinds of heat treatments today. So in that way, we can affect the microstructure and thus affect the strength of the material. But the elimination as such will not be a big contribution to any strength increase. Here we have an example on the effect of fatigue properties. So this is data for EBM Ti-6AI-4V. And here we can see the as printed data, and then we have the HIP data. And if we compare these two at the amplitude stress of 600 megapascals, we can see that we get around 10,000 cycles out of the as printed material, and for the same stress level, we get around 400,000 cycles for the HIP material. For the same data set, we can see how the hipping affects the scattering or reduction of scattering. So here we can see the as printed material, and for the HIP material, we can see that the scatter band is much smaller. Another example when it comes to reducing scatter for AM material, this is for an EBM printed Inconel 7 and 18, and here we're looking at the hardness of the material. So we can see that there is quite a big scatter here in the hardness in the as built condition, and this is, in this case, it's between different samples from the same build. And then we can see by doing HIP or combined HIP and heat treatment of this material, we can reduce this scatter to a very, very small, narrow scatter band. And here's just to show an example why we can see this different scatter and variation in AM. And here's an example for an EBM printed Ti-6AI-4V. And we're looking at here 3 identical samples produced in the same build, but they have been built at different positions on the build plate. And if we can see, the amount of porosity and especially the positioning of the porosity here varies quite a lot between these different samples. And of course, we can imagine if we're eliminating all these porosity by hipping, we can assume that we get the reduction in scattering of properties as well. If we look at the basics of the defect elimination by hipping, one thing to notice is that only internal defects is eliminated by hipping. Any surface connected porosity or feature where the pressure medium can penetrate will not be eliminated by hipping. So a gas tight surface of your sample or of your components is required. And this is normally not an issue for powder bed fusion. You will have a gas tight surface unless you're using very crazy printing parameters. If we're looking at binder jet material, it has to be sintered to high enough density to get gas tight surface, and that threshold is normally around 92% relative density in the as printed state. So this is where the porosity goes from a more communicating characteristic to a more isolated characteristics. The shrinkage in the HIP process will correspond to the amount of densification that we're achieving. So one example, if we have 2% porosity in our material and we HIP it to 100% density, we will have a 2% shrinkage by volume of our part or sample. And that corresponds to 0.67% linear shrinkage in each direction. And the shrinkage will be homogeneous if the porosity is homogeneously distributed in the material. So now I want to discuss different type of defects in powder bed fusion material, and also why it's good to know the characteristics of these different defects when it comes to hipping. So we can have gas porosity originating from the powder particles itself. So they are created pretty much when the powder is atomized. We see some examples up here. So these are cross-section of powder particles. So here, for example, we can see a particle with a gas pore inside that was formed during the atomization. And these gas pores in the powder will actually stay in the as printed material. So for example, here we can see one of those porosity that's remaining in the as printed material. Depending on what gas we're using for the atomization process will be whatever these pores are filled with. We can also have lack of fusion defects or keyholing defects that are formed during the actual printing process. And if we look at the EBM systems, which are processed under vacuum, these defects will contain vacuum. If we look at the laser powder bed fusion systems, where you normally use argon or in some cases nitrogen, then of course these kind of defects will be filled with either argon or nitrogen. And vacuum porosity will be completely eliminated by hipping. So for example, a lack of fusion defects form in EBM printing. Also nitrogen porosity will also be completely eliminated by the HIP cycle. The nitrogen will actually diffuse into the metal when we're hipping, so we can completely eliminate it. If we look at argon, that's a gas which is not reactive, and it's a quite big molecule or atom. So that gas will actually not diffuse into the metal. And so in the case of argon porosity, the hipping will reduce the pore size a lot below detectable limits. However, the pore is actually not completely eliminated. So since the argon is still there, and since we're decreasing the size of the pore a lot, we will actually have high pressure argon inside the pore. However, this is not something new. We have had this kind of argon porosity in powder bed fusion material since the beginning of this process. And we know that the fatigue properties is very much improved by the HIP process. So it seems like the size of the porosity in the as printed stage is big enough to actually affect the fatigue properties. But when we HIP them to a very much smaller size, they won't affect the fatigue properties as much anymore. That's why we see this fatigue performance increase by hipping. But if we have this high pressure argon gas inside the pores, what happens with the pores in the material when the material is heat treated after hipping? This is a question that's been asked in the AM industry today. And there's not much research that has been performed in this topic yet. The phenomenon is called thermal induced porosity, and it's pretty much that if we have a high pressure argon inside the pore and we heat up the material so it gets softer, there's a driving force for the pore to start to grow. And there's a quite good paper from the University of Sheffield looking at this topic, which I will go through now in the following slides. And they have been printing EBM Ti-6AI-4V samples. And then they've been evaluating these specimens with X-ray CT scanning in different stages. So they've been looking at the as-printed condition, the as-hipped condition, and also hipped samples that they've then heat treated at elevated temperature in a non-pressurized environment. And then they've been comparing the amount and size of porosity in each condition. So here we can see the same sample in the different conditions. So we can see here in the as-printed condition, we have some porosity, some are quite large. In the as-hipped condition, we can see no porosity at all. The detectable limit of porosity with this CT scanner is 5 micrometers. So anything we can't see here is below 5 micrometers. However, then they have done a heat treatment at 1035 Celsius in a vacuum furnace. And here we can actually see that some of the porosity, or we can see some porosity here that we couldn't see in this step because it's too small. If we look at the same temperature but at 10 hours instead of 10 minutes, we can see pretty much the same, maybe a little bit increase in size of the porosity. But this tells us that it's not too big difference between these two samples. Tells that it's more a mechanism of mechanical deformation more than creep. They've been also looking at 1200 degrees Celsius, where we can see a little bit bigger porosity here. Here they actually been able to identify one single pore and look at that in all the conditions. So this is the same pore in all conditions, and we have the as printed pore here. Then we hip it, and it's as small so we can't detect it. And then we can see after heat treatment it enlarges a little bit. One thing to notice here that even after 10 hours at 1035 Celsius, we can see that the pore, it doesn't grow to its initial as printed size. So some conclusions from this paper is that the argon-filled pores will decrease in size by hipping a lot. However, they will not be completely eliminated. And that argon pores can grow a little bit when we're doing post-heat treatment after hipping at a non-pressurized environment. However, they don't grow to their initial as-printed size, but around 1/3 to 1/4 of the initial size they showed in this study. This was EBM printed material, and what they could see that the lack of fusion defects did not regrow at all. And that's because since they are under vacuum, they will be completely closed, and there's no driving force for these defects to grow when we heat treat after hipping. And one quite important thing to notice here also is that with high pressure heat treatment, when we combine the heat treatment in the hipping under pressure, this type of thermal induced porosity can be avoided. So here's an example of how we can avoid this type of thermal induced porosity. So this is for an Inconel 718 material. And here we have incorporated the full heat treatment cycle in the HIP cycle, in the HIP and under pressure. So in this case, there's no risk of any thermal induced porosity, and there's no need to do any heat treatment after this cycle. Okay, so now I'm going to go through a case study on optimized HIP parameters for EBM Ti-6AI-4V. And just as a background, I want to look a little bit on the HIP parameters for AM material. So one thing to notice is that, of course, the main purpose of hipping is to get to 100% density to eliminate all the porosity in material. However, there will be different parameter sets that will take you there. So there's not one unique HIP cycle for an alloy. You can use different HIP cycles and still get to 100% density. Another thing to notice is that powder bed fusion microstructure are often quite different from conventional microstructures. However, today in the AM industry, we're normally using HIP cycles and heat treatment cycles, etc., taken from more conventional manufacturing methods like casting or forging, for example. So one question to ask is are these HIP parameters really the the best for AM material to give optimal results. And we have been doing a study together with Arcam to kind of look at this topic a little bit. So Arcam had been looking at hipping, and they saw that they get the increased fatigue properties, they got the increased ductility, and the reduced property scatter, etc., which was good. However, they also saw that they got some decrease in yield strength when they were hipping. So we can see an example here on the right, where we have a tensile curve for, this is actually SLM Ti-664, but it shows a good example. So we have the as-built material here, and then when we hip the material with the standard hip cycle, which is here, we can see that we get a significant drop in yield strength here. And this is, of course, maybe not the best for most applications. So we have done a study together with Arcam to investigate this. And why do we get this reduction in strength when we're doing the hipping? So in the EBM or SLM process, we have very high solidification rates, and this gives us very fine microstructure in the as-printed condition. And this very fine microstructure gives us quite hard strength, high strength. And any elevated temperature processing after the printing, for example, hipping, will give you a coarser microstructure because of it's elevated temperature at a certain time. And this will give us a decrease in strength. So we can see an example here. We have as printed Ti-664 material, and for the same type of material that has been hipped, we can see that we get a coarsening of the microstructure. And if we look at the typical practice for hipping today for this material, we have the ASTM standard called F292414, which is for powder bed fusion Ti-664. And in this standard, they're specifying a hip temperature between 895 to 955 degrees Celsius, 100 megapascal, and minimum 2 hours. And the typical hip cycle used within this standard is 920 degrees C and then 100 megapascal 2-hour hold time. And this cycle is developed 30 years ago for castings, and this is what we're using for AM material today. But we wanted to see if we could address this problem and try to decrease this drop in strength we get for when we're hipping. And the approach we were taking was to look at lower hip temperatures to try to affect the microstructure less. So we can see here we were doing the standard hip cycle as a reference, and then we were going down all the way down to 800 degrees Celsius we were looking at. And here we can see the results of that study in terms of yield strength and elongation. So we can see the strength of the as-built material here. And as expected, we can see with the standard hip cycle, we get this drop in yield strength that we have already seen. Which was interesting to see then, which was quite encouraging, was that when we were reducing the hip temperature here all the way down to 800 degrees Celsius, we can see that we get an increase in strength. One thing that we also saw was that at 800 degrees Celsius and 100 megapascals, we saw that there was a tendency that we didn't get full densification. And that was, of course, a requirement for all the hip cycles, that we have to get full densification, because that's, of course, the main purpose with the hipping. But we also did the same temperature and cycle, but with 200 megapascal pressure instead. And then we actually saw that we got 100% density to fulfill that requirement. We could see that the elongation was pretty much the same for all material, all variants. So some conclusions for this study was that just by tweaking the hip parameters a little bit, we could get higher strength in our as-hip material and the best overall material properties. A more general conclusion is that powder bed fusion material is something different from conventional manufacturing processes. So we might not be able to just copy heat treatment recipes or hip recipes or whatever from any other industry and think that it will give us the optimal results for our material. I also want to mention that we have seen the same results also for laser-based powder bed fusion material. However, that study I can't show, but we saw the same results for that material as well. And also, since we see here that hipping can affect the microstructure, the as-printed microstructure, it's pretty good to have that in mind when you're doing your development of your material or printing parameters, that if you're going to do a HIP cycle afterwards, it might change the microstructure. So that's something to have in mind. Today in the AM industry, there are investigations going on looking at what is the best HIP practice for powder bed fusion Ti-664. So, for example, we have this standard HIP cycle, which is performed at 920 degrees Celsius. We also have this approach for low temperature hipping that I just showed you, that we can increase or we can get higher strength with that type of cycle. Another approach is to HIP above the beta transverse temperature of the material. The purpose with this HIP cycle is to be able to erase anisotropy in the microstructure and also in the properties. When we're looking at this high HIP temperature, we probably need rapid cooling from that temperature and down. And Oak Ridge National Laboratory is looking at this kind of cycle right now, so I hope to get some good result out of that soon. We can actually see some early results from that their work here to the right. So up here we have the typical columnar microstructure of a EBM printed Ti-664, and this is a completely equiax microstructure after above beta transverse hipping. We're also going to investigate actually the full age hardening heat treatment for Ti-664 combined in the HIP cycle to see if we can achieve the maximum strength. As a second part of this study, we also was looking at optimized printing parameters for hipping. And just as a background, I want to mention that the final density after hipping will be 100% dense, undepending of the start density, as long as we have a gas-tight surface of our parts or of our samples. So one example is here we can see here we actually printed just a capsule in an EBM machine. So we're printing a shell and we left powder completely loose and unprinted inside. So here we can see the actual sample. We could HIP it to 100% density, as we can see here. So in this case, as long as we have a gas-tight surface, which we have in this case, we can go to 65% density, which is pretty much the tap density of the powder, to 100% density by the HIP process. And this is quite an extreme example, but it tells us, it shows us what is possible to do with hipping. So this tells us that it is possible to allow a higher amount of porosity in the as-printed condition if we know that we're going to HIP or that we decide that we're going to HIP. We will still have 100% density after hipping. So this is also something we investigated together with Arcam, where we're using a printing strategy with less energy input. And what Arcam did is that they increased their line offset or hatch spacing from their standard 0.2 millimeter to 0.4 millimeter instead. And here we can see the densification results with that printing strategy. So in the lower left picture here, we can see the samples analyzed with the layer cam. So in the left picture here, we have material printed with the standard parameters, and we can't really see any porosity at all here. With the increased line offset, you can see that we have quite a lot of porosity. The bright fields here are the porosity. And to note here also that the outer perimeter of the specimens were actually printed with the standard parameter. So that's completely gas tight, so it's possible to HIP without any encapsulation. On the right here, we can see the effect of hipping on the densification. So even the material with this porously printed material, as we will call it, actually had 8% porosity, as we can see here. But with the HIP cycles, we can restore it completely to 100% density. And here we can see the results in terms of mechanical properties. So we have the as printed material with the normal printing parameters, and then we have the as printed material with the porous printed parameters, as we call it here. And we can see that we actually get higher strength even though we have 8% defects in the material. So that's quite interesting. However, we can see that we also have very bad elongation since we have 8% defects in the material. But we can also see that with the HIP cycles, we can actually restore this bad elongation to normal values. And if we look here with the porous printed material and the optimized HIP parameters for this material, we can see that we get to really high strength here. So in this case, we're actually higher than the as-built normal strength. The purpose of this study from the beginning was to try to reduce the drop in strength from this value, and now we could actually produce material with slightly higher strength than that. And why do we get higher strength when we print with more porous printing parameters? Well, since we have less energy input to the material, we have a smaller melt pool, so we will have less remelting of the layers, and that gives us a finer microstructure, which we know gives us higher strength. And we also have less aluminum evaporation during the printing because of this smaller melt pool. We can see those results here. So in the as-built normal condition, we have 6.2% aluminum, and in the as-built condition with the porous parameters, we get 6.5% weight percent aluminum. And this also has some contribution to the strength increase. So from this second part, we conclude that we could conclude that 8% porosity in the sample can be completely eliminated by hipping. So it's possible to allow more defects in the as printed condition and remove all of it by hipping in the end. So question is, why would you print to 99.5% density or above if you're doing a HIP cycle afterwards? So this was quite interesting that we saw that we can get increased strength when we're printing with less energy input. However, after this study, I think we realized that there might be even more interesting benefits with doing this approach. Here I've listed two quite major challenges for a metal additive manufacturing. So it's a relatively slow manufacturing process, as we know. It's quite costly process for mass production. And this is one of the big hurdles for full industrialization of powder bed fusion, that it is a quite slow process. You need many, many printers to do a mass production of parts. Another thing is thermal stresses. This is especially for the laser-based powder bed fusion processes. And the thermal stresses that we get during our build, that will actually limit the possible build size and build the design of your part, for example. And also you have to work with thermal management in the build process with supports, etc., to be able to transfer heat away from the build. And now I'm going to show you how HIP can help to overcome these challenges. So with the same approach I just mentioned, that HIP will densify the material to 100%, so we can allow ourselves to have a higher amount of porosity in the as printed condition, and it's possible to print with a less energy input. And this enables higher process speed in the printing process. So we can use, for example, increased scan speeds when we print, or increased line offsets or hatch spacings when we're printing. And this will give us shorter print times and thus increased productivity. Also, since we're using less energy input to the material, we will actually reduce the thermal stresses in the printing process. So we can reduce the work around thermal management of our build. And also it might enable printing of designs and sizes of parts that is not even possible to print today. Here I'm going to show some data taken from a paper written by Dominik Alers at the Paderborn University in Germany. So this shows how much time it's actually possible to save in the printing process by allowing a higher amount of porosity in the as print condition. So on the vertical left axis, we can see the relative density. On the right axis here, we see the time reduction in the printing process. And on the x-axis, we can see the volume energy density in the printing process. The blue bars here is the relative density as built. The red bar is the relative density after hipping. And then we can see this black line corresponding to time reduction. So for example, here we can see that they printed one specimen set with only 94% density. It was possible to get to 100% density with the HIP process, and we can see that we can save over 50% of the printing time by doing this. So now I will summarize this third webinar of ours, and we have seen that HIP gives improved properties for AM material, so improved fatigue performance especially, and also reduced property scatter. We have seen that different types of defects in AM material can be good to know the characteristics of those defects when it comes to hipping. For example, are the defects under vacuum or are they gas filled? Because this can have an influence on the HIP and post-HIP heat treatment. We have seen that the standard HIP cycles used in industry today might not always be the optimal HIP cycles for AM material. And it's possible to optimize HIP parameters for AM for best outcome. We have also seen that it's possible to use hipping to speed up powder bed fusion production rates and also to reduce thermal stresses in the powder bed fusion building process. So since this is the last webinar of our three-parted webinar series, I will also summarize the webinar series as a whole. So in the first webinar, we saw that the main industry segments using HIP are aerospace, medical, energy sector, and automotive industry. We have seen that high pressure heat treatment, that is when we're combining HIP and heat treatment in one cycle in the HIP. And the main purpose of this is to reduce process steps and reduce and eliminate process steps. We could see that some process benefit with high pressure heat treatment are reduced cycle time, lead time, energy consumption, capital investment, and cost. And that we also get excellent process and quality control when doing everything in one equipment in-house. We have seen that modern HIP systems, they are safe and easy to use. We can achieve very high cooling rates in a modern HIP system, up to 8,000 Fahrenheit per minute. And that we have a high degree of flexibility that makes it possible to tailor-make high-pressure heat treatment recipes for optimal and desired properties of your material. All these three webinars, there will be a recorded version, and these versions can be accessed either via the link that you have gotten in your emailed invitation, but also on our YouTube channel, and our name on YouTube is just Quintus Technologies. So the first and second webinar recorded version are already on YouTube, and I think this recorded version will be there sometime tomorrow. And just to wrap it up, I will mention again that the Quintus team will be at Rapid this year. We will have a booth there, number 509. So you're very welcome to come up to us during Rapid and ask any question you have about hipping, etc. Also, if you want to have a more focused sit-down meeting with us, feel free to reach out to us and we can book a meeting during this conference. Yeah.
All right. Well, thank you so much, Magnus, and thank you for everyone for joining us today. We are now going to begin answering the questions that were submitted during today's presentation. As a reminder, you can still submit questions through the questions pane in your attendee control panel. So our first question is Pablo, and his question is, in case of AM parts, do you recommend removing them from the build plate before the HIP process?
That's a good question. And I mean, it's very possible to HIP the AM parts on the build plate. And you can also incorporate the stress relief in the HIP cycle. And it's mainly determined by the size of HIP system you need. So if you have the build plate, if you have the parts on the build plate, of course you need a HIP that can fit this build plate. It depends a little bit on what annual volumes you're looking at to HIP and the size of HIPping. So if you remove the parts from the build plate, you can of course use a smaller HIP system to HIP those parts, and you might be able to have a better fill packing density or fill ratio in your HIP cycle when you run it. But it's very possible to do it on the build plate. It's also possible, of course, to do it off the build plate. So it's kind of depends on the HIP size and how you want to run your process. Yeah.
Okay, thank you for that. Jim asks, when printing with more porosity, does it equate to a shortened print time?
Yeah, I mean, the examples we have seen so far, we have seen that we can reduce the print time quite a lot. And I think this is very interesting. And I hope that we can do some studies on this during the year here to show more results. But of course, if you don't really have a requirement on high density in the as printed stage, we can speed up the scanning process. We can use a larger line offset or hatch spacing, and that will speed up your printing process.
And then Benedict asks, are not most PBF systems running with argon? Why is this not as good as nitrogen?
Let's see, are not most laser powder bed fusion systems running with argon? What is not as good as nitrogen? So I mean, most laser powder bed fusions are running under argon, and the difference between argon and nitrogen is that the argon won't diffuse into the metal. So we will reduce the porosity size a lot to below detectable limits, and we know that this gives us very good fatigue properties. If you use nitrogen, the nitrogen will actually diffuse into the metal, so the porosity will be completely eliminated. We can't regrow them or anything after HIP. However, you will have diffused nitrogen into the material, so that might be an issue or a drawback for some materials, and for some materials it's not an issue to have nitrogen diffused into the metal. So yeah, that's pretty much what I can comment on that.
Okay. Thank you. Dave asks, why is thermally induced porosity not an issue when doing the heat treatment in the HIP?
That's because, I mean, the whole thing with the growth of pores, again, after HIPping, that is that we have high pressure argon in these very small pores. And then when we heat up the material in a pressureless environment, we will decrease the yield strength of the material. So there is a driving force for these high pressure pores to open up a little bit. And that's why we get pores if we do a pressureless heat treatment after HIPping. However, if we do the heat treatment in the HIP, we will do it under pressure. So the pressure will actually it will hold back this growth of pores. So it will be pretty much as a normal HIP cycle. When the material are cooled down, it gains its strength, and then we release the pressure, and the pores won't grow.
Okay. Peter asks, does using HIP mean that you can use more standardized powder?
I think, I mean, if you look at, I think since we can allow a higher amount of density in the as printed condition, I think that you might be able to have less requirements on the powder itself. So, but that's a good question and something very interesting to investigate.
Okay, thank you for that. Another question is from Aiden. During the LMD process, it is possible to have retained austenite due to built-up type. Do you think that it is possible to decrease the retained austenite by high-pressure heat treatment?
Might be. I don't really know how to answer that question, really. But I mean, we can. But it depends on what the retained austenite, why we get the retained austenite. But I mean, we can get very high cooling rates in the HIP. We can cool down to room temperature, so pretty much similar to any other quenching methods. So to try to get our martensite or whatever we want. Yeah.
Okay. Our final question is from Liang. How about the closed crack during the following heat treatment steps? Reopening like a pore or a crack?
So any internal crack will not reopen after hipping. Any surface crack, any surface connected porosity or crack where the pressure medium can penetrate, then nothing will happen after hipping. But it depends what you have in that crack. Do you have vacuum in the crack? Do you have argon in the crack? Do you have nitrogen in the crack? If you have argon, if you have vacuum or nitrogen in the crack, it will not have any risk to reopen after hipping, even though we're heating up the material at elevated temperatures. If we have argon in the crack will actually spherodize when we hip it and be very, very small. And if we would regrow with a post-hip heat treatment in a pressureless environment, it will not regrow as a crack. It will regrow as a sphere, and that's of course much better when we're looking at fatigue properties.
Okay. Well, thank you so much, Magnus, for answering our questions, and thank you to everyone for attending today's webinar. You will also receive a follow-up email within 48 hours with a link to view a recording of today's webinar. On behalf of Quintus Technologies, thank you for joining us today and for our entire webinar series, and have a great rest of your day.